The world all around us is just swimming in invisible electronic signals. We're talking Wi-Fi, radio, 5G, GPS, the whole shebang. But what if you could actually see them? What if you could reach out and measure them? Well, that's exactly what a spectrum analyzer does. And in this explainer, we're going to pull back the curtain on this amazing tool and show you just how it makes the invisible visible.
Okay, so to really wrap your head around what a spectrum analyzer is all about, it really helps to compare it to a tool you probably already know, the oscilloscope. Now, an oscilloscope shows you a signal in what we call the time domain. You see how its voltage goes up and down from one moment to the next. But a spectrum analyzer, it shows you that exact same signal in the frequency domain. Instead of asking how, it asks what. What are the individual frequencies that make up the signal, and how strong is each one? It's a totally different way of looking at things, and it is incredibly powerful.
Here's a great way to picture that difference. In the time domain, all the different frequency parts of a signal are just mashed together. But in the frequency domain, they're all pulled apart. Think about an entire orchestra playing a big, loud chord. An oscilloscope is like hearing that one combined sound. The spectrum analyzer, though, that's like seeing the sheet music. It separates out and shows you every single note from every single instrument that's making up that chord.
So how in the world does this thing perform the magic of separating all those frequencies? You might think it just, scans through them one by one, but the reality is so much more clever than that. It's not about brute force. It's about an elegant engineering solution that I like to call the frequency shifting trick.
This trick we're about to look at, it solves a huge engineering problem. Just think about it for a second. How do you build a single filter that can be precisely tuned across this massive range of frequencies? From just a few hertz all the way up to billions of hertz. Trying to build a filter that's stable and accurate over that kind of range is, it's insanely difficult and crazy expensive.
So what's the answer to that incredible challenge? How did the engineers solve it? Well, the brilliant and kind of surprising short answer is they didn't. They didn't build that filter at all.
Right. Instead of building a super complex filter that moves, the engineers completely flipped the problem on its head. They figured out that it's way easier to build one perfect, super accurate filter that stays fixed at a single frequency. And then they just cleverly shift the entire signal you're trying to measure past that stationary filter's little window.
The name for this frequency shifting technique is heterodyning, and it is a fundamental concept in pretty much all of radio technology. Basically, it works by mixing your incoming signal with a second signal that's generated right inside the analyzer. This mixing process lets you effectively slide the entire frequency spectrum up or down. By carefully controlling that second signal, you can move any part of the spectrum you want to see right into the crosshairs of your one perfect fixed filter.
So here's how that process works in 3 basic steps. First, an initial filter just gets rid of any signals way outside the range you even care about. Second, your signal gets mixed with a tunable signal from something called a local oscillator, or LO. This is the key frequency shifting step. And finally, that one perfect fixed filter, the intermediate frequency, or IF filter, analyzes the result. By sweeping the LO's frequency, you're sweeping which part of your input signal gets shifted into the view of that IF filter. And that is how the analyzer creates its scan.
Okay, that is enough theory for now. Let's get practical. How do you actually drive this thing? We're going to go over the 4 essential settings you absolutely need to master to navigate the spectrum.
First up, you've got center and span. This is your basic navigation. Think of it like a map. Center frequency sets the middle of your screen, and span sets how wide your view is. So, are you looking at an entire city, or are you zooming way in on a single street? You just put the signal you're interested in right in the middle, then adjust the span to see what's happening around it. Simple as that.
Next up is the reference level. Now this one is crucial. It sets the power level for the very top line of the display. You want to adjust it so your signal's peak is sitting nicely near the top to get the best view. But, and this is a big but, you got to be careful. If your signal goes above this level, you can overload the analyzer's super sensitive input, and that will create distortion and give you completely false readings.
And now for what is honestly the most important setting of all. Resolution bandwidth, or RBW. This is the actual width of that fixed IF filter we talked about. It's the window that's effectively scanning the spectrum. A narrower RBW is like using a magnifying glass. It gives you incredible detail, and it lets you see 2 signals that are really close together. But, as we're about to find out, that amazing detail comes at a cost.
And finally, there's video bandwidth, or VBW. Now, people get this confused with RBW all the time, but it is completely different. VBW is a filter that gets applied after the measurement is already made. Its only job is to average or smooth out the noise that you see on the screen. It doesn't help you separate signals or anything like that, it just makes the display look cleaner.
And that brings us to the single most important practical concept you need to master when you're using one of these things: the resolution trade-off. This is all about the constant battle between getting a really detailed measurement and getting a fast one.
And it all comes down to that one setting we just talked about. To put it simply, for basic spectrum measurements, resolution bandwidth is, by far, the most important setting. I mean it. Getting your RBW right is the absolute key to getting a good, accurate measurement. This slide lays out the dilemma perfectly. On one side, a narrow RBW acts like a microscope. It can separate signals that are right next to each other, and it lowers the noise floor, which lets you see really weak signals. The result? Incredible detail. The cost? A very, very slow scan. On the other side, a wide RBW is lightning fast, but the trade-off is that it kind of blurs signals together and raises the noise floor, hiding all that fine detail. So you always have to ask yourself, what do I need more, right now, detail, or speed? And let's just look at how powerful that effect on the noise floor is. The relationship here is really predictable and super useful. As you can see on this chart, every single time you decrease the RBW by a factor of 10, so going from 3 MHz down to 300 kHz, the average noise level you see on the screen drops by about 10 dB. This is the main trick you use to dig very weak signals out from all that background noise.
So we've covered the what, the how, and the how-to. Let's wrap things up by talking about the why. Why does decoding this invisible world of signals matter so much in our world today?
Well, who actually uses a spectrum analyzer? The answer is pretty much everyone in electronics. We're talking wireless engineers designing your Wi-Fi and 5G networks, broadcast technicians making sure TV and radio stay on the air, aerospace and defense folks working with radar and satellites, even technicians whose whole job is just to hunt down sources of electronic interference. For all of these people, it is an absolutely essential tool.
At the end of the day, what all of these professionals need is exactly what the spectrum analyzer gives them: a clear and precise window into the otherwise chaotic frequency spectrum. It makes the invisible visible, and it makes the unmeasurable measurable.
So I'll leave you with this final thought. The air all around you, right this very second, is an absolute ocean of signals. You've got Wi-Fi, radio, your cell phone, Bluetooth, everything. If you had a spectrum analyzer in your hands right now, what would you look for first?